This is a recast of the 6,800-word piece, Deep Key Networks, DQNs, from Schneepat.com. This article discusses the concept of deep key networks, DQNs, and how they have become a powerful technique in reinforcement learning. It covers the components, theoretical foundation, applications, advancements, and challenges of DQNs. Let's listen in.
Today we'll be diving into the world of deep key networks, or DQNs, and exploring how they have become a powerful technique in reinforcement learning. Reinforcement learning is a subfield of machine learning where an agent learns to make decisions by interacting with an environment and receiving feedback in the form of rewards or punishments.
That's right, Ben. DQNs combine deep neural networks with Q-learning, which is a popular algorithm in reinforcement learning. This combination allows an agent to learn optimal actions in complex environments. The key innovation of DQNs lies in the use of a neural network to approximate the Q value, which represents the expected cumulative reward for taking a specific action in a given state.
Exactly. And this neural network used in DQNs consists of multiple layers of interconnected neurons, enabling it to learn complex patterns and representations from raw input data. This makes DQNs capable of handling high-dimensional and continuous state spaces, which is a significant improvement over traditional key learning algorithms.
DQNs have found extensive applications in various domains. For example, in healthcare, DQNs can be used to aid in medical diagnosis and treatment planning. The deep learning capabilities of DQNs can provide more accurate and efficient results, leading to improved patient care.
That's right. And DQNs are also valuable in robotics and autonomous systems. By using DQNs, robots can learn and make decisions based on their environment, enhancing their capabilities to perform complex tasks.
Absolutely. And gaming is another field where DQNs are extensively used. Intelligent agents developed using DQNs can learn and adapt to play different games, making them versatile tools for problem-solving and decision-making scenarios.
So now let's take a look at the components of the deep key network, DQN algorithm that improve its stability and convergence. One of these components is experience replay, which addresses the problem of correlated samples. By storing experiences in a replay memory buffer and randomly sampling from it during training, the DQN algorithm reduces the correlation between consecutive samples and improves learning efficiency.
That's an important point, Ben. Another component is the target network, which is a separate network that is periodically updated with the weights of the main network. This provides more stable Q value estimations and helps in reducing the overestimation bias that can occur in Q learning algorithms.
Absolutely. And then there's the epsilon greedy policy, which balances exploration and exploitation during training. This policy selects random actions with a small probability, allowing the agent to explore different actions while also exploiting the actions that have shown to be successful.
And lastly, the Bellman equation is used to update the Q values based on the observed rewards and predicted future rewards. This equation plays a crucial role in reinforcement learning algorithms, including DQNs, as it allows the agent to learn from its experiences and improve its decision-making process.
Now that we have covered the components of DQN, let's talk about the theoretical foundation of DQNs. Reinforcement learning is a type of machine learning where an agent interacts with an environment to maximize a reward signal. Key learning is a popular algorithm in reinforcement learning that estimates the quality of actions in a given state using a key function.
And in DQNs, this Q function is represented by a deep neural network. The use of deep neural networks allows DQNs to handle high-dimensional state and action spaces and learn effective representations of the game or environment. This makes DQNs capable of tackling complex tasks.
Exactly. And to enhance the learning process and improve generalization, DQNs leverage experience replay and target networks. Experience replay helps in stabilizing learning and reducing overfitting by randomly sampling from past experiences. Target networks provide more stable key value estimations by periodically updating the weights of the main network.
And there you have it, folks. Deep Q networks, or DQNs, are a powerful technique in reinforcement learning that combine deep neural networks with Q learning. They have found applications in various domains, including healthcare, robotics, and gaming. The components of the DQN algorithm, such as experience replay and target networks, enhance its stability and convergence. And the theoretical foundation of DQNs lies in reinforcement learning and Q learning algorithms, which allow agents to learn and make decisions based on their environment.
Absolutely. The goal of reinforcement learning is to optimize decision-making processes by discovering the optimal actions to take in different situations. And DQNs achieve this by utilizing deep neural networks to estimate the quality of actions. This allows for more accurate and flexible representations of the action value function, overcoming the limitations of linear function approximation.
That's right. And one of the major advantages of DQNs is their ability to learn directly from raw sensory input. This eliminates the need for handcrafted feature engineering, making them suitable for complex tasks such as playing Atari games. By learning from high-dimensional data, DQNs can tackle problems with large state spaces and nonlinearity.
And another key advantage of DQNs is the utilization of experience replay. This technique stores transitions in a replay buffer and samples mini batches randomly. This mitigates the issue of correlated data and helps reduce the variance of updates, enhancing the stability and rapid convergence of the learning process.
Absolutely. And let's not forget about target networks. By periodically updating the weights of the main network, target networks provide more stable Q-value estimations. This further enhances the overall performance and effectiveness of DQNs.
Right, and it's important to note that despite the remarkable success of DQNs, there are still areas for improvement and ongoing research to optimize their performance. For example, enhancing the exploration-exploitation trade-off and addressing overestimations are challenges that researchers are actively working on.
That's true. And these advancements in DQNs have revolutionized the field of reinforcement learning. By combining deep neural networks with Q-learning, DQNs have made significant advancements in artificial intelligence. They offer improved performance and wider applicability in various domains, from healthcare to robotics to gaming.
Definitely. And it's all thanks to their ability to learn directly from raw sensory inputs and their utilization of experience replay and target networks. These advancements have allowed DQNs to tackle challenges such as nonlinearity and high-dimensional state spaces, enabling agents to make better decisions and achieve higher rewards.
Absolutely. And with ongoing research and improvements, DQNs continue to evolve and hold promise for solving even more complex tasks in the future. The combination of deep neural networks and reinforcement learning has opened up new possibilities for artificial intelligence.
Right, and one of the key components of a typical DQN is its structure. It consists of an input layer, one or more hidden layers, and an output layer. The input layer receives the raw state information, which is then passed through the hidden layers. These hidden layers perform calculations using activation functions like rectified linear unit, ReLU, allowing the network to learn complex representations and hierarchies of states.
That's correct. The output layer of the DQN produces Q values, which represent the expected cumulative rewards for each possible action. These Q values are used to select actions based on a policy that optimizes the network's performance over time.
Exactly. And when it comes to neural networks in DQNs, they play a crucial role in approximating the optimal action value function. Neural networks are computational models inspired by the functioning of the human brain. In the context of DQNs, they allow the network to map environmental states to their respective action values, enabling informed decision-making based on learned knowledge.
Right. And deep neural networks, which have multiple hidden layers, are particularly effective in extracting high-level features from input states. This complex arrangement of nodes and interconnections allows for more expressive and accurate approximations of the action value function. It facilitates the optimization and utilization of the Q-learning algorithm.
And let's not forget about how DQNs learn and update their Q values. There are two techniques involved: experience replay and target networks. Experience replay involves storing the agent's experiences in a replay memory buffer, including state, action, reward, and next state. During training, many batches of experiences are randomly sampled from this buffer to train the network. This helps maintain a diverse and representative training set.
Absolutely, and target networks use a separate network with fixed parameters to calculate the target Q values. By periodically updating the target network's parameters to match the current network's parameters, stability in learning is enhanced. This decoupling of target and current networks mitigates the issue of oscillation or divergence during training. Combined with experience replay, DQNs effectively learn and update their Q values, leading to improved performance and more efficient reinforcement learning.
Right, and it's worth noting that DQNs have been successfully applied in various complex domains beyond traditional video games. They have shown promise in robotics, enabling autonomous agents to learn and adapt to their environment through reinforcement learning. Researchers have demonstrated improved performance in tasks like grasping, navigation, and object recognition.
And in natural language processing, DQNs have been effective in language translation, sentiment analysis, and dialogue systems. The ability of DQNs to learn directly from raw sensory data without the need for handcrafted features or domain-specific knowledge makes them an attractive choice for tackling complex and dynamic real-world problems.
Absolutely. And lastly, let's talk about the training process of DQNs. There are two fundamental principles involved: experience replay and target networks. Experience replay addresses the issue of correlated updates and non-stationary distribution of training data. By storing transitions experienced during interactions with the environment and a replay buffer, sequential correlation between data points is broken, allowing for more efficient learning.
That's right. And the target network is a separate network that provides the training targets for the main network. These targets are updated infrequently to stabilize the learning process and reduce the potential for divergence. By combining experience replay and target networks, DQNs overcome the challenges of training deep reinforcement learning algorithms.
Exactly. And let's not forget about the pre-processing techniques that are crucial for preparing input data for DQNs. One common technique is normalization, where the input states are scaled to have similar ranges. This prevents any particular feature from dominating the learning process and allows for shared representations across different states. Another technique is frame skipping, where the agent's action is repeated over multiple frames. This reduces redundant observations and speeds up training without compromising the underlying features.
Right. And another important pre-processing technique is frame stacking, where consecutive observations are stacked as a single input frame. This helps the agent capture temporal dependencies between frames and improves its ability to perceive motion. By implementing these techniques, DQNs can effectively process input data and enhance the learning process.
Absolutely. Now let's talk about the balance between exploration and exploitation in DQNs. This is a crucial challenge in deep reinforcement learning. Exploration refers to the agent's ability to try out new actions and explore different parts of the environment to gather more information. Exploitation, on the other hand, involves the agent's tendency to exploit the current best strategy based on its knowledge.
That's right. One popular strategy for balancing exploration and exploitation is epsilon greedy exploration. In this strategy, the agent randomly selects a non-optimal action with a small probability, epsilon, and selects the current best action with a high probability, 1 minus epsilon. This allows the agent to explore new actions while also exploiting its current knowledge to maximize rewards.
However, determining the optimal value for E is not easy and often requires careful tuning. Striking the right balance between exploration and exploitation is crucial for achieving optimal performance in reinforcement learning tasks.
Moving on, let's discuss some of the limitations and challenges of DQNs. One major issue is their high computational requirements, which makes them computationally expensive and hinders their adoption in real-time applications.
Absolutely. DQNs also struggle with tasks that require long-term planning as they heavily rely on short-term memory. Additionally, they are sensitive to their initial conditions and have a tendency to converge to suboptimal solutions.
Another challenge is the lack of interpretability in the decision-making process of DQNs. Their complex network architecture and internal representations make it difficult to understand the reasoning behind their actions.
That's definitely a challenge, but there have been advancements in addressing some of these challenges. For example, double key learning and dueling DQNs have shown promising results in improving the stability and learning efficiency of DQNs.
That's true. Double key learning helps address the issue of overestimation and value estimation, which can lead to suboptimal decision-making. And dueling DQNs separate the estimation of the state value and the advantage value, allowing for more accurate value approximation.
Absolutely. Further research and innovations are necessary to overcome these challenges and enhance the overall performance of DQNs in real-world scenarios. Moving on to the next point, one of the major challenges faced by deep key networks is dealing with high-dimensional input data. Traditional algorithms struggle to handle the enormous amount of data involved in complex tasks like image recognition and natural language processing.
That's right. But DQNs have revolutionized the field of artificial intelligence by employing deep neural networks that can effectively process high-dimensional input data. By using convolutional and fully connected layers, DQNs are able to extract meaningful features from raw input and learn the underlying patterns and structures.
And this ability of DQNs to handle diverse and complex input data has opened up possibilities in areas such as autonomous driving, robotics, and healthcare.
Absolutely. DQNs have found applications in various domains, showcasing their versatility and effectiveness. In robotics, they have been used to train agents that can navigate complex environments, manipulate objects, and perform tasks that were previously challenging for machines.
And in finance, DQNs have been employed to optimize trading strategies and forecast market trends. In healthcare, they enable the development of intelligent systems for disease diagnosis, drug discovery, and personalized treatment recommendations.
Furthermore, DQNs have shown promise in the field of game theory, allowing for the creation of intelligent game-playing agents that can compete against human experts and facilitate the development of advanced strategies.
The vast range of applications of DQNs highlights their potential to revolutionize various industries and improve problem-solving capabilities across different domains.
Absolutely. Now let's talk about some recent advancements and improvements to DQNs.
One notable advancement is the introduction of the double DQN algorithm. It addresses the issue of overestimation bias observed in traditional DQNs by utilizing a separate online network to select the best actions and a target network for value estimation. This allows for a more accurate and stable learning process.
Another significant improvement is the incorporation of prioritized experience replay. This approach assigns higher probabilities to experiences with larger temporal differences, focusing learning on crucial portions of the state space. It improves data efficiency and reduces sample complexity.
And let's not forget about dueling DQNs, which have been introduced to handle greater complexity in state value and advantage estimation. By independently estimating the value and advantage functions, dueling DQNs enable better generalization and more efficient learning.
These recent advancements lay the foundation for the continued development and refinement of DQNs, paving the way for their effective utilization in a wide range of complex tasks.
And speaking of utilization, DQNs have gained significant attention in recent years due to their ability to learn and make decisions in complex environments.
That's right. DQNs combine Q-learning and deep learning techniques to approximate the optimal action value function from raw sensory inputs, such as pixels in a game screen.
And they employ an experience replay mechanism, where past experiences are stored and randomly sampled during training. This leads to improved data efficiency and reduced sample complexity.
The effectiveness of DQNs has been demonstrated in various domains, showcasing their potential for tackling real-world problems.
Absolutely.
That's right. DQNs have also been utilized in development of robotic systems for healthcare, elder care, and search and rescue missions. This highlights their potential in real-world applications. By integrating DQNs into robotic systems, we can create intelligent robots capable of acting in dynamic and uncertain environments.
Moving on to another domain where DQNs have shown promise is in financial modeling and stock trading. Stock market prediction and algorithmic trading strategies rely on sophisticated models that are continuously evolving to capture and capitalize on market trends. By incorporating DQNs into existing financial models, traders and investors can potentially enhance their decision-making and optimization procedures.
That's correct. DQNs have the ability to learn from past data and make predictions about future market conditions. This offers a valuable tool for intelligent trading systems. With their computational power, DQNs can process enormous amounts of data and analyze intricate patterns that may not be easily discernible to human traders. Furthermore, their adaptive nature allows them to promptly adapt to dynamic market conditions, providing real-time insights and increased efficiency in stock trading.
Absolutely. And it's not just robotics and finance where DQNs have proven effective. They have also been applied in other domains such as natural language processing, NLP. By integrating the DQN framework with NLP techniques, models have been trained to generate coherent and contextually appropriate responses in conversations.
That's right. DQNs have also shown promise in the field of healthcare. They have been used to develop intelligent systems for diagnosis, treatment recommendation, and disease prediction. This demonstrates the wide range of domains where DQNs are making significant contributions, showcasing their versatility and potential impact in various fields.
The effectiveness of DQNs can be attributed to their ability to learn directly from raw sensory inputs, eliminating the need for manually engineered features. By employing a deep learning approach and utilizing artificial neural networks, DQNs approximate the Q-value function, allowing them to make accurate decisions in complex environments.
Exactly. By incorporating convolutional neural networks, DQNs can automatically detect meaningful features from visual inputs, providing a more comprehensive representation of the state space. This not only increases the model's ability to generalize across diverse scenarios, but also enhances its responsiveness to changes in the environment.
And let's not forget the revolution that deep learning techniques have brought to reinforcement learning algorithms. The use of deep learning in DQNs has showcased the immense potential of machine learning in solving complex real-world problems.
While DQNs have proven effective in many domains, it's important to note that they also have their limitations and criticisms. For example, they have shown sensitivity to hyperparameter settings, making them challenging to train effectively. The choice of network architecture, learning rate, and exploration strategy can greatly impact the network's performance.
That's a great point. Another limitation of DQNs is their struggle with continuous action spaces. Their discrete nature restricts their applicability to tasks requiring fine-grained control.
And let's not forget about the sample inefficiency of DQNs. They often require a vast amount of data to converge, limiting their applicability to real-time and resource-limited scenarios.
That's correct. These criticisms call for further research and improved methodologies to address the limitations of DQNs.
Absolutely. Despite their limitations, DQNs have shown immense potential in various fields and continue to be an exciting area of research.
One major concern raised in the article is the issue of sample inefficiency and computational requirements when training DQNs. Since DQNs learn from experience and need to explore the environment, they require extensive interaction, which can be time-consuming and computationally expensive.
That's right. The article mentions that recent advancements such as prioritized replay and parallelization techniques have been proposed to improve sample efficiency and reduce training time. These techniques aim to optimize the learning process by prioritizing important experiences and distributing the computational load across multiple processors.
Additionally, the article highlights the computational requirements of training DQNs, often requiring powerful hardware like GPUs. This can be a challenge for users who may not have access to such resources. The researchers suggest that further research is needed to make DQNs more accessible and applicable in various domains.
Yes, that's an important point. Making DQNs more accessible to a wider range of users would greatly expand their potential applications. It would also enable researchers and developers with limited resources to contribute to the field of reinforcement learning.
Moving on, the article also addresses ethical considerations and potential risks associated with DQNs. It emphasizes the need for careful consideration of ethical implications when deploying DQNs in critical sectors such as healthcare or finance.
Absolutely. The article raises concerns about automated decision-making by DQNs inadvertently discriminating against certain groups or propagating biased behavior learned from biased training data. This highlights the importance of developing robust frameworks that prioritize fairness, interpretability, and security when implementing DQNs.
The black box nature of DQNs, where their decision-making processes are not easily interpretable, is another ethical concern mentioned in the article. Without clear explanations for their decisions, it becomes challenging to understand and address potential biases or unintended consequences.
Furthermore, there are potential risks associated with adversarial attacks, where malicious actors manipulate or exploit DQNs for nefarious purposes. This could include misinformation dissemination or sabotage. The article stresses the need for responsible and ethical use of DQNs with a focus on developing frameworks that prioritize fairness, interpretability, and security.
Absolutely. These ethical considerations are crucial in ensuring the responsible deployment of DQNs in real-world scenarios.
Now let's discuss potential alternatives and future directions in reinforcement learning. The article suggests that incorporating unsupervised learning techniques with DQNs could enhance their capabilities.
That's right. By allowing the agent to learn from unlabeled data, unsupervised learning could lead to more efficient and versatile learning. This could open up new possibilities for DQNs in solving complex tasks.
Additionally, the integration of multi-agent reinforcement learning is another potential direction mentioned in the article. This would enable the development of intelligent systems capable of collaborating with other agents towards achieving common goals.
These potential alternatives and future directions hold great promise for advancing the field of reinforcement learning. They offer novel opportunities for developing more robust and intelligent agents.
Let's now discuss some techniques that have been proposed to improve the stability and convergence of DQNs during training. One notable approach is experience replay.
Experience replay involves storing observed transitions in a replay memory and then randomly sampling from this memory during network updates. This reduces the correlation between consecutive training steps, allowing for more efficient learning.
Another technique that has been successful in stabilizing DQNs is the use of target networks. By introducing a separate target network with delayed updates, the Q values used to compute the loss are more consistent, leading to improved training.
The concept of reward clipping has also been suggested to mitigate the impact of large positive rewards that can cause instability in the learning process. By capping the reward magnitude, the DQN can better generalize and learn effectively in various scenarios.
These techniques contribute to improving the stability and convergence of DQNs during training, making them more reliable and efficient.
To wrap up, the article concludes by discussing the significance and potential of DQNs in the field of reinforcement learning. DQNs have emerged as a powerful tool, showcasing remarkable advancements in artificial intelligence.
Their ability to handle high-dimensional state spaces and generalize knowledge from one task to another has proven to be a game changer. DQNs have surpassed human-level performance in various domains, including gaming, robotics, and autonomous vehicles.
However, there are still challenges that need to be addressed, such as sample inefficiency, training instability, and exploration-exploitation trade-offs.
Future research should focus on addressing these limitations and exploring additional advancements to enhance the performance of DQNs in various applications.
Absolutely. The potential of DQNs is immense, but further advancements and research are necessary to unlock their full capabilities.